Hello everyone, welcome back to our lecture course Quality Management and Applied Statistics with Ulrich Weber. This is the first lecture and we're talking about descriptive statistics, and in this video we want to talk about data and what we can extract, what we can learn from data that we are given. Let's first have a look at what types of data there are. There's ordinal data, so data that can be ordered, has an inherent order in it, like rolling a dice. 1 to 3 can be put in order, or temperatures, prices, things like that. There's also nominal data, so things that don't have an order, like gender or blood groups. We're not gonna spend a lot of time with those types of data. Just keep in mind there are some restrictions. For example, we can't, later on when we talk about averages, calculate an average blood group. That doesn't have any meaning whatsoever. So that's only for ordinal data. So with the data, we sometimes get a load of raw data. So think of a die, we get numbers 1, 4, 6, 2, 1, and so on. And it can be a long list of data. That's raw data. And I call the raw data the xi's, so x1, x2, x3. Yeah, first, second, third outcome. It isn't always the best way to look at data because it's very big and bulky and confusing. We can assemble data, so it makes sense if you think about a die to think in terms of possible outcomes. So we know possible outcomes are only the numbers between 1 and 6. 1, 2, 3, 4, 5, 6. And I call those the AJs. So my possible outcomes, 6 of them. We can do that also with like nominal data. Important is that there's only a finite number of those, or a number small enough so we want to look at them individually. If we have sort of infinite amount of possible outcomes, or such a large amount of outcomes that it doesn't make sense to look at each individual one, we can also group things into intervals with ordinal data. So for temperatures, for example, we could say we just take ranges. We say, I don't know, 0 degrees Celsius, 20 degrees Celsius, 40 degrees Celsius, and now I'm only interested in the range within these sorts of brackets. Yeah, so we've got like 1, 2, 3, 4 outcomes now. Yeah, these intervals. Gonna talk about that later again. Okay, the big advantage of having these lists of outcomes is you can talk about frequencies. So instead of the long list of raw data, I can say, okay, my number, thinking about the die, my number 1 happened 5 times, number 2 came 9 times, number 3 times, and so on. Yeah. So I can condense my data into like these 6 numbers, and it contains a lot of information. What I've written here are the absolute frequencies. So absolute mean the exact number of occurrences. In like a mathematical way, I basically sum over all my xi's. So from I equals 1 first outcome to the last outcome xn, and every time my outcome is equal to the outcome of my outcome list, so every time there is a, let's say, a 4 on my die, I add 1 to that sort of category, that bin. You don't need to remember that formula, I just want to like write it down in a formal way. I think it's pretty clear what we're doing. So yeah, the absolute frequencies in this example list here says how often did my 1 come, and I had 1 1, like 1 2, no 3s. Yeah, we can see that in the list here on the left, that there's the 1, there's the 2, and we didn't get a 3. If we just have absolute numbers, that might not tell us a load, because it depends on how often I roll the dice. So if I say like I got 3 20 times, then how often did I try to get a 3? So we can calculate relative frequencies. I call them Hj. So I normalize my absolute frequency by the number of total attempts, or number of total data points. So here I've got 5 data points, 1 2 3 4 5, so n equals 5. So if I divide my nj's by 5, I get my relative frequencies. And we can think of the relative frequencies in terms of percentages. So I could say 20% of the time I got a 1, 40% of the time I got a 6. Yeah, because they're normalized, so the sum of them adds up to 1. They add up to 100%. One interesting thing about these frequencies is, if we later on we talk about distributions, probability distribution, then these relative frequencies, they are our best guess for the empirical mass density function. So like a sort of probability density function for a random variable. But that's just to mention now. I'm going to talk about that later. So there's the direct correlation and the picture. So by saying in 20% of cases we get a 1 from our die, that could define a system that always reacts like that. Unless we know any better, that's our best guess. The only slight issues, what happens if we don't have a limited number of outcomes and we're working with intervals. The problem is, if I don't have intervals all the same size, if you look back up here, I've got 1 2 3 4 5 6 outcomes, and sort of like each outcome has the same importance, the same weight, the same weighting. But if I look at intervals, for example, I choose my intervals to go from 0 to 0.5, then from 0.5 to 2, 2 to 5, 5 to 10, 10 to 20, then you see here at the bottom that the intervals have like completely different sizes. That in itself is not a problem, but then if we use the relative frequency as a probability density, we would get this blue graph here. So here I've just drawn Hj, and that is sort of a problem, because if my interval was not from 10 to 20 but from 10 from 10 to, let's say, 40, then this rectangle here become twice as big, and that would like change our probability distribution, because we'll later see that's the area, that's the integral over it. So we're running into a problem there. We can fix it quite easily if we normalize. So the right formula is, if you're working with intervals, we have to normalize the relative frequency by the width of the interval. So I've shown this here in green, and you see now the empirical density function kind of goes down. There, the O points are the blue dots, but this one is going down, and that makes a lot of sense because, you know, the big, although this interval from 10 to 20 is huge, we only got like four hits within this interval. Yeah, and this tiny interval from 0 to 0.5 got 3 hits. So the density must be a lot higher here in this narrow interval. Yeah. So that's just a bit of a side remark. It will make more sense after lecture 4 when we talk about distributions. Okay, now up to you. Little exercise. So you toss a coin 8 times and obtain this following result. Now please create a table for absolute and relative frequencies for the coin toss, and I'm always going to do it on the video like that. I'm going to ask you to do something, then pause for a few seconds, then show you the result. So if you want to do that in your own time and like think about it, pause the video and then resume once you've got your result. Okay, so this is the table. We've got 2 possible outcomes. Either we're having heads or we're having tails. There's not much more to it. I can, if I want, identify them with numbers, so I can say heads is a 1, tails is a 2, but it doesn't really matter at this point. The main thing is I've got 1, 2, 3, 4, 5 heads. Yeah, so 5 heads and 3 tails, and in total it's like 8 coin tosses. So that makes a relative frequency of 0.625 for the heads and 0.375 for the tails. Let's try another example. So we record wind direction in degrees, where the wind blows from, and I've got these 5 angles here, and we want to use like some intervals with like 45 degree distance, so 0, 45, 90, 135 degrees. Create a table for this one as well, please. Perfect. Here we go. So these are my AJs, 0, 45, 90, 135, and for each interval within those I get results. So between 0 and 45 I've got this one, and this one. So 3 is my absolute frequency. In total 5 data points, so 0.6 or 60% that the wind comes from that direction. And yeah, and then the others also make sense. So that's the sort of first obvious steps. If you wanna work with data and count frequencies, you can use Excel. For most of the things we do, it has sufficient calculating power, and it's a lot of people prefer it because it's quite like obvious what you're doing. So you can use the command COUNTIF to calculate your frequencies. If you want to work a bit more advanced, you can use MATLAB, which is freely available for HM students. So here we've got the command hist counts, and I can explain to you how MATLAB works in more detail another time, or use the online help. It's quite powerful and has a lot of examples in it. Okay. So these were the frequencies. Now let's talk about cumulative frequencies, and they work for ordinal data only. So what we do is we have the relative frequencies and we just sum them up. So let's look at our data table here in the example. So I tossed my die 5 times. I got 5, 2, 6, 6, 1. That's my outcome. I can identify my 6 outcomes, they're the AJs. These are my absolute frequencies. And now I can create my cumulative absolute frequency. That's a bit of an odd one. We won't need that very often. Basically, okay, I got 1, 1. Brilliant. They're always the same. Then this number here tells you how many 2s or less I had. So kind of for this one here, or put in a different number, I add those 2 together. So that's 2. And then for the next one, for this one, I add those 3 together, and so on. And you probably get it, like for number 4 there's no change either, but then for the 5, this one, that's all these 5 numbers together, I get a 3, and then for this last one I add all of them. And obviously what has to be here is the number n, the number of attempts or data points. So basically from left to right, in ordinal data, I just add the numbers. I can do the same thing with the relative frequencies. So instead of raw numbers, I add percentages, or these numbers smaller than 1, and obviously they add up to 1. This one always has to be 1 at the right side. The interesting thing about the cumulative relative frequencies is that it's also the best guess for the empirical distribution function. Those of you who already are familiar with distribution functions, basically the distribution function that we get here is our best guess how the model works that produced our data points in the first place. And we get an estimate of that here. So what we did for the die, for example, here is our relative cumulative frequency. And if I just put that into a graph, so here is 1, 2, 3, 4, 5, 6. And then I just put the numbers in. So at 1 I get 0.2, at 2 I get 0.4, then it stays on 0.4, and then at 5 it jumps to 0.6, and then it jumps to 1. So this is our distribution function. We're going to see, like, if it's a fair die, every number has the same probability, then over time this would smooth out and produce a nice triangle. But yeah, we don't have enough data to see that, and more about this later on. So let's just give it a go. it's your turn. So we roll the die 4 times and get the following result. Please create a table with the cumulative absolute and relative frequencies. Well done. So basically we have the table here, 6 outcomes between 1 and 6. 1, 2, 2 times the 4, 1 times the 5. So if you do the cumulative frequency, 0 ones, 1, 1 and 2, and no 3, so no change. Then it goes up to 3 because we've got 2 4s. Then it goes up to 4. Here is n. And the same with the relative frequencies. So instead of 1 we've got 25%, and here it jumps to 75, and then we're at 100. Brilliant. If you want to do that on Excel, just sum over the frequencies with sum command, and the MATLAB offers you the function cumulative sum. Alright. Next video will be about averages. See you in a sec.